Let us analyze how interrupt entrance and stacking sequence happens. Now, according to the ARM architecture procedure and call standard, that is, it's called AAPCS. So it's a standard. A C function can modify registers R0 to R3, R12, R14, which is the link register, and the PSR, okay, program status register, without having to save the contents prior to using them. That is, when there is, say, there is a thread that is executing and an interrupt occurs. When the interrupt service routine is entered, these registers R0 to R3, R12, R14 and PSR can be used without having to worry about whether their contents are lost or not. That is, the contents of these registers are automatically saved before entering the subroutine or entering the interrupt subroutine. Okay, but generally, if you are coding in C, the compilers are free to only stack those registers which it is using. So it is not necessary that to save all the registers in one shot. That is for a function call. That is, if you are calling a particular subroutine from another subroutine, you are free to only save those registers among these what we saw in the stack. But in the case of interrupts, all the registers are saved. There is no, because an interrupt service routine will know which registers among these are actually being used. So all the registers are saved by default in the case of an interrupt service routine. Now, these registers are called caller saved registers according to the AAPCS standard. Now, register R4 to R11 are called call E saved registers. Okay, so they must be saved by the function if the function intends to use this register. So suppose I go to I am executing a subroutine from main. I can freely use R0 to R3, R12, R14 and PSR, but if I intend to use R14 to if I intend to use R4 to R11, it is my responsibility to save these first on the stack, then use these registers, restore them before exiting the particular function, and so that the caller function gets these registers in the same state as it had when before it called the second function. Okay. Now, the interrupt mechanism in ARM closely resembles a normal function call with a few differences. Like I mentioned, the mechanism saves all the AAPCS caller save registers as against only the ones required. Okay, and the link register, which stores the return address of the function, has a different value which is called exc return in the case of an interrupt. Okay, it will not save the program counter. It will save some other value which we will soon see. Now the reason is the interrupt needs to consider a lot of factors, because as we know, the interrupt can get into privileged mode, it can get into unprivileged mode in thread, and there are a few other things that needs to be considered. For example, whether the floating point registers were used, so the stacking will be different, and so on and so forth. Okay, and also the stack pointer to choose, the process stack pointer or the main stack pointer, the privilege level of, for example, whether it's a privileged or unprivileged execution, and so on and so forth. So link register is different. The PC, of course, the program counter or the return address is saved on the stack instead, because the link register has a different set of values. The program counter is saved on the stack instead of the link register. Okay. Now the block of data. So we will not separately discuss the stack frame for a function, because if we discuss the stack frame for an interrupt, it actually explains how the stack frame for a function works. It is just a subset of this. So describing the stack frame here will also cover how the stack frame is utilized for a function call. So the block of data that is pushed onto the stack memory is called a stack frame. Now, for Cortex M3 and M4 processors, say without floating point unit, that is, I would say without floating point unit or without using the floating point unit, even if the floating point unit exists, is always 8 words, that is 32 bytes. Okay, that's the size of the stack frame. For Cortex M4 with floating point unit, the stack frame can be either of 8 or 26 words depending on the lazy stacking mechanism. We spoke of the lazy stacking mechanism. So it could be either 8 or 26 words depending for the lazy stacking mechanism. Now let us come to the interrupt entry and stacking sequence, and we will just go through an animation, and we will try to understand what is going on in here. So we saw this previously. This is the register bank, so R0, R1, R2 to R12, and you have stack pointer that is R13, which is banked. So you have the MSP, it's the main stack pointer, and the process stack pointer. You have the link register, which is the which in actuality normally saves the return address, and R15 register 15 is the program counter, and then you have the program status register. This is the stack. So the stack is an area of the RAM, which it's an area of the RAM which is used by the interrupts and used by different subroutines to store their local variables, so on and so forth. So the stack is a very important structure in the case of all possible computation that we know of. Okay. To begin with, we see that the previous stack grows downward. So whatever address the stack started with during reset, the addresses actually decrease as far as stacks are concerned. So if it say it starts from 100, it goes, when the stack gets filled up, it goes 99, 98, 97, 96, something like that. So the stack grows downwards. If this is the increasing address, the stack grows downwards. So let's assume that this is the last stacked item. So there is the previous stack is here. Whichever function has left a stack, it is here. And the blue arrow is actually indicating that this address location is held here. So R13 holds the address location of this particular place, this particular memory region, or memory location, not region, I'm sorry, memory location. Okay, so this is the start of an interrupt execution. So nothing has happened so far. This is when you are entering an interrupt, the hardware sees this. Then it starts executing the interrupt entry and the stacking process. So next stage, what it does is, the red arrow stands for, it saves the XPSR into the next location in the stack, one address less. Okay, so it goes down one address and saves this value from here. So the XPSR is still there, the value is still there, the value is copied here, and now the stack pointer is pointing to this location. Okay. Next, the return address, that is the program counter, instead of being in the link register normally, it is pushed onto the stack. One more address increases, and the return address, the stack pointer now points to where this memory. Then the link register is saved. Link register, so same process happens. Link register is saved, and now the stack pointer is, the blue arrow is indicating that the stack pointer is here, is pointing to this. Then R12 is saved. Okay, so it's following the AAPCS standard. R12 is saved, stack pointer points to the region where you have R12. Then R3 is saved. So R3 is copied over here and the stack pointer points to this location. Then R2 is saved. R2 is saved. Stack pointer pointing to where R2 is. R1 is saved. R0 is saved. So it has saved all the registers. So how many items? 8 items. 1, 2, 3, 4, 5, 6, 7, 8. This was the last stacked item. So according to the APCS standard, it has saved 8 items on the stack. Now it does something. At this stage, the link register is populated with one of these values. Now, generally, the link register will be populated with the return value of the caller function. But in the case of interrupts, it is different. Now, if you have a look at this table, there are 6 possible values that the link register can be filled with. Now, the table is divided into 2 halves. The top half is when floating point is not used. So it may not be used due to lazy stacking, where the floating point unit is enabled but it's still not used. And the other scenario could be that the floating point unit is not even enabled in hardware. So in that case, these 3 values are going to be used. If the floating point unit is used, then the lower 3 values are going to be used. Now, why do we need to have the link register populated with a different set of values for interrupts, whereas in the case of a normal subroutine, we could just get away with putting the return address of the caller function? Now, whenever an interrupt is called or whenever an interrupt is event happens in the case of Cortex M4, the processor has to keep track of quite a few things. For example, when the interrupt is working on a different mode, as we know, the interrupt works so the processor switches to the handler mode when the interrupt is executing. Now, from the handler mode, it has to come back to the thread mode. Now, and when it has to come back to the thread mode again, it has a choice of which stack pointer it was using. It could be the main stack pointer or it could be the process stack pointer. So it has to remember all of this while returning from the ISR. So to do that, instead of saving the program counter in the link register, it has to save this number, and the program counter instead is saved onto the stack, as we saw. Now, let us go through these values one by one and see what they stand for. So here when we are not using floating point, we could have this value, that is 7F and 1, and this signifies return to handler mode. Exception return uses non-floating point state from main stack pointer, and the execution uses main stack pointer after return. So the main stack pointer is being used after return, but in this case, this exception, whatever we are seeing currently, has actually happened within another exception. That is, probably this is a higher priority exception which has preempted the previous one, right? So in such a scenario, we are going to have this value in the link register. Now we are going to have this value in the link register, that is all Fs and 9, when you return to thread mode and exception uses a non-floating point state, as we are in the non-floating point section of the table, from the main stack pointer, and the execution resumes at main stack pointer. So this is a this is a common scenario where the interrupt has occurred when we are within a, say, privileged thread mode. This one is when return to thread mode, but use the PSP. Okay, so that is when the return when the return from the thread mode happens, then not the main stack pointer but the process stack pointer is going to be used. So during branching, the process stack pointer was being used, so the control has to use the process stack pointer on return. All of this is without using the floating point. Now when the floating point is being used, then the values are different. That is, instead of the last but one F, it is E. So again, from it is the same as this one, but this time using a floating point, that is return from MSP to MSP. Okay, that is within an exception. There is an exception to an exception. This is from a thread exception back to a thread using MSP in both the cases, and this is PSP in both the cases. Now, why do we need a separate set of values for floating point being used? That is because the unstacking and the stacking for floating point is different. That is, in the AAPCS standard for floating point, many more registers need to be saved. So about 26 registers. These numbers take care of that. Let's move on. So this after this, of course, there is the interrupt vector fetch. So the controller is going to go into the exception vector table and it is going to fetch the exception vector. Now the exception vector could be say it is a UART interrupt. Now for the UART interrupt ISR vector, that vector is fetched from the exception vector table and that vector address is put into the program counter. Okay, so now the program counter points to the interrupt vector location of that particular interrupt that has been raised. Now all of this is happening in the hardware, so there's no code for this. All of this happens in the Cortex M4 core. Now again, we come to the interrupt exit and unstacking sequence. So now let's assume that the ISR has completed executing. Now when the ISR has completed executing, then again this table, the same table that we saw previously, it is the time now that this table is actually going to be used to figure out where to return to, in what mode to return to, and which stack pointer to use. So I repeat, what mode to return to and which stack pointer to use, either with floating point enabled or floating point not enabled. So with floating point enabled, the unstacking sequence is different from floating point not enabled. The number of registers are different. The number of registers are more in the case of floating point being enabled. Okay, so we see the first thing that happens during the unstacking sequence is the program counter gets loaded with the EXC return value. Now please notice that EXC return and question mark has been added here. So mind it, this EXC return value, when this ISR is returning, may not be the same as what is loaded onto the program counter. So where does this value come from? So when the interrupt is entered, definitely the EXC return value is stored in the link register. So no doubt about that. So this part, okay. But when the ISR gets over, that the linked register might not have the same EXC return value. It might have it or it might not have it. Okay. So we will discuss why this happens. It's a very simple reason, but we'll come to that. So now the program counter gets loaded with exe return either directly from the link register or from somewhere else, which we'll see now. Once the exe return value comes into the program counter, that is when the Cortex-M4 processor knows that this is an interrupt return. So it's a beautiful mechanism actually, where the Cortex-M4 processor treats the ISR like an ordinary function. So only when it sees the exe return value, that is this bit pattern, does it know that this function is actually an interrupt return, not a general return from any other function, non-interrupt function. Okay. Now why does this exe return value change, and why is it that not always can the exe return value be loaded from the link register? So it's very common. This is something very common for function handling in general. Okay, so suppose the ISR calls another function, and that happens quite often. Though we are supposed to keep the ISR quite brief, sometimes we might call a small function from an ISR. Now, when the any function from an ISR gets called, so when a function gets called from another function, obviously, of course, the LR value at that stage is going to be overwritten, because we are doing a BL and switch to the other function in assembly. So when the LR value gets overwritten, we had exe return here. So the exe return value will be lost. But what the compiler does in that case is, by default, whether it's an interrupt service routine or not, it saves two values. So R7 is a register which the GCC compiler generally uses for stack pointer manipulation, and it saves the link register onto the stack if any function, including the ISR, is calling another function. So you will see that at that time the return instruction, so when the ISR is calling another function, then if you look at the disassembly of that particular ISR code, you will see an instruction like pop R7 PC. So it would have been push R7 and LR before, just when the ISR would have been entered. Now, so we will see some disassembly and it will become more clear to us as to what really happens. So this code actually, you will see, depending on whether a function is calling another function or not, the style of return changes. If it's calling another function, the return looks like pop R7 PC, else it becomes BXLR. BXLR would mean then the compiler is assuming that the return address or whatever is in the link register. If even for an ISR, if the ISR is not calling any function within its body, it is going to be BXLR, because at that time LR is going to retain the exe return value. And this is true for all function calls, just not ISRs. Okay. Going forward, now this is the exit. So exit sequence begins here. Exe return value from the link register or the stack into the program counter, and the stack pointer is pointing to this location of the stack. So now the first part is the R0 is copied back to the main register R0. That is, the R0 value on the stack is copied back, and the stack is still pointing here. In the next stage, R1 is copied back and the stack pointer is pointing to R1. Next stage happens with R2. Same procedure. R3, R12, okay, R14, okay. So now the link register gets filled with R14. So the program counter, the processor knows what needs to be done. So it may or may not return the exe return value. Okay, and then the return address is filled to the program counter. So the program counter till before this was containing the exe return value till a while ago. Now it is not needed, and then it is overridden by the return address here. Okay, and then the XPSR is also copied over, and stack pointer points to XPSR, and finally the last stacked item is SP comes back to the last stacked item which we saw before, and then there is a return to function as the program counter holds the address of the next instruction from where the branch to the ISR happened. In the case of a floating point, the same process repeats, but so imagine the same process happening, but in the case of floating points, the number of registers are much higher. So as you can see, it not only saves the registers that we saw previously, but it also saves the floating point registers and then floating point status register and everything. So the number of registers saved is much higher. Therefore, the latency, interrupt latency in the case of floating point unit being used is much higher, and that's the reason we have the concept of lazy stacking, where if the floating point unit is not used, then it is going to only save the previous set of registers that we saw, thus saving a lot of clock cycles. Now coming to interrupt latency refers to the delay. So we've been talking about interrupt latency, right? So we said that about floating point units not being used amounts to lazy stacking, or when you have tail chaining. All of these are ways to reduce interrupt latency. So by definition, interrupt latency is the delay from the start of the interrupt request to the start of the interrupt handler execution. Okay, so interrupt latency includes processes like stacking the registers, vector fetching instructions, and interrupt handler. So we saw all of this in the previous animation, right, where we saw the whole process. Without any latency, regular interrupt latency is about 12 clock cycles and 29 clock cycles with floating point turned on. Okay, so this is the standard time. Now interrupt latency is increased beyond usual time by the following factors. So suppose the processor is carrying out some memory transfer, okay, including buffered write operations and so on. This transfer has to be completed before the exception sequence starts. Okay, so obviously it adds to the latency. If the processor was serving another exception at the same or higher priority, of course, adds to the latency, because that interrupt has to get over before this interrupt can start executing. You're using a debugger. If you're using a debugger, then it kind of locks everything up, so no interrupts can work. So if you're using a debugger, then it definitely adds to the latency. The processor was carrying out an unaligned transfer. So from the processor point of view, there might be a single access, but at the bus level, it takes multiple cycles as a bus interface. So you are doing an unaligned transfer, say maybe it's not 4-byte aligned, you're just doing a transfer of some addresses aligned to maybe 1 byte or 2 bytes, not 4 bytes. So it has to convert that unaligned transfer into multiple aligned transfer, and that adds to the latency. Okay. Another factor that adds to the latency is the processor is carrying out a write to a bitband alias. So bitband is again memory regions where you can directly access without read, modify, write. You can just directly access the bits. So that is called bitband alias. So whenever a bitband operation is happening, the internal bus, so even if you do a bitband, internal bus actually has to convert into a read, modify, write sequence only. So which at least takes 2 cycles before the interrupt can start its process of stacking and vector fetch and so on.